At the farthest reaches of the observable cosmos, astronomers have identified a beacon of staggering antiquity, MOM Z14. This faint smear of light is not just another distant galaxy. It is, as of mid-2025, the most ancient galaxy ever observed by humanity, a remnant from the dawn of time itself. To grasp its place in history, consider this. The Big Bang occurred 13.8 billion years ago, and MOM Z14 formed only about 280 million years after that fiery beginning. In cosmic terms, that is practically the first breath of the universe, when darkness was just giving way to light, and the first structures were attempting to form amidst chaos. What makes this so breathtaking is not only its age, but the fact that it still shines across the gulf of time, its photons traveling unbroken for 13.5 billion years before colliding with the mirrors of the James Webb Space Telescope. When we look at MOM Z14, we are not looking at a distant object frozen in space. We are peering into a time capsule, directly witnessing the universe's infancy. This discovery strikes at something deeply human, the longing to understand origins. Every civilization has asked the question, where did it all begin? For thousands of years, the answers were confined to myth, speculation, or philosophy. Now, through the power of modern astronomy, we can stare across the abyss of time and see the evidence written in starlight. MOM Z14 is not a distant point of trivia. It is a piece of our own story. It represents the first organized structures that would eventually pave the way for galaxies like our Milky Way, for stars like our Sun, and ultimately, for planets like Earth. Without the pioneers of light like MOM Z14, the path to our existence may never have unfolded. The staggering nature of this discovery lies in its temporal placement. Astronomers often refer to this as peering into cosmic dawn, a time when the fog of the early universe was lifting, and the very first stars and galaxies flickered into life. To detect a galaxy from this early age is equivalent to hearing the heartbeat of the cosmos right after its birth. We are not observing something comfortably ancient, like a dinosaur bone that is millions of years old. We are staring at something that predates the Earth itself by billions of years. When MOM Z14 formed, the Earth was not even a thought in the universe's future. The Sun was unformed. The Milky Way had not yet taken shape. And yet, in that formless era, this tiny galaxy was already collecting stars, pulling together matter, and shining against the darkness. What makes this even more gripping is the sheer improbability of such a find. Detecting something this faint, this remote, and this ancient is like trying to catch the flicker of a candle across an ocean. MOM Z14 doesn't scream its existence. It whispers through stretched and faded light, redshifted almost beyond recognition. Without the James Webb Space Telescope, this galaxy would have remained hidden, swallowed by distance and time. Its discovery is a triumph not just of technology, but of persistence, the result of humanity's centuries-long dream to see farther and deeper than our naked eyes could ever allow. But perhaps the most profound element of MOM Z14's story is its symbolism. Here, in a fragile assembly of stars at the edge of detectability, lies proof of how quickly order can arise from chaos. In only a few 100 million years, the universe managed to cool, condense, and organize itself into galaxies, massive systems of stars and matter bound together by gravity. This timing is astonishing because it compresses what we once thought required vast stretches of time into a narrow window right after the Big Bang. It is as if the universe, having just emerged from its explosive birth, wasted no time in crafting complexity. For astronomers, MOM Z14 is more than a record-breaking galaxy. It is a challenge, a riddle, and a guidepost. Its existence demands answers to pressing questions. How did such a galaxy form so quickly? What does this imply about the density of matter in the early universe? And could there be others even older, hiding just beyond our reach? Each of these questions expands into 1,000 more, pushing science to refine its models and stretch its imagination. The awe that accompanies MOM Z14 comes from both its factual importance and its poetic weight. To sit on a small rock orbiting an ordinary star and yet be able to glimpse a galaxy formed nearly at the beginning of everything is almost surreal. It speaks to the peculiar brilliance of humanity, that a species so fleeting can find a way to measure eternity. In the faint glow of MOM Z14, we are not merely seeing another galaxy. We are seeing a mirror of beginnings, a fossil from the earliest chapter of the universe's unfolding story. A silent reminder that we are connected not just to our Earth, not just to our Sun, but to the very moment when light first emerged in the void. What makes MOM Z14 stand apart from all other galaxies discovered so far is not just its antiquity, but the extreme conditions under which it was detected. Astronomers measure the remoteness of galaxies not in miles or kilometers, but in a property called redshift. The higher the redshift, the farther back in time and space the light has traveled. MOM Z14's redshift is Z equals 14.44, a staggering figure that pushes the limits of what we thought was even possible to observe. This number is not arbitrary. It represents the degree to which the universe has expanded since the light left that galaxy. At such a colossal redshift, the light from MOM Z14 is stretched so much that it lies far beyond the visible spectrum, deep into the infrared. To put this into perspective, even galaxies with redshifts of around Z6 or 7 are considered incredibly ancient, dating to when the universe was less than 1 billion years old. The famous glass Z13 galaxy, once hailed as the oldest, had a redshift of 13. Now, MOM Z14 surpasses that record with ZT equals 14.44, plunging us even further back in time, into an age when the universe was still in its cosmic infancy. Detecting a galaxy at this threshold is akin to finding the first page of a book thought to have been long lost. It gives us a rare glimpse into a time when cosmic structures were just beginning to emerge. What makes this redshift so unique is that it sits near the very edge of what astronomers thought JWST could see. The telescope was engineered with incredible sensitivity to infrared light, designed specifically to probe the earliest epochs of the cosmos. But even so, the discovery of MOM Z14 stretches its power to the maximum. Detecting light that has traveled for 13.5 billion years is no trivial task. Over that immense span of time, the photons have been stretched, weakened, and nearly drowned out by the cosmic microwave background and interstellar dust. Yet, JWST's instruments were able to capture this faint whisper of ancient starlight and confirm its authenticity. Another factor that makes MOM Z14 special is how faint it truly is. Astronomers describe its brightness as being on the edge of detectability, almost at the noise floor of JWST's detectors. It is so dim that without the telescope's unparalleled resolution and stability, it would have been indistinguishable from background static. That faintness underscores just how extraordinary this achievement is. MOM Z14 is not a blazing beacon like a quasar, but a fragile, almost invisible ember from the universe's youth. And yet, that ember has survived the journey across time to reveal itself. The uniqueness of MOM Z14 also lies in the scientific boundaries it challenges. For years, cosmologists built models predicting how fast galaxies could form after the Big Bang. According to traditional theory, galaxies this early should not have been so organized, so bright, or so massive. The prevailing assumption was that it would take hundreds of millions of additional years for enough gas and dust to coalesce into recognizable galactic structures. And yet here it is, a galaxy fully formed at only 280 million years after the beginning, staring at us from the abyss. This forces us to rethink whether star formation and galaxy growth were more rapid than believed, or whether our models of cosmic evolution need to be fundamentally altered. Beyond science, there is a symbolic uniqueness as well. MOM Z14 shows us the razor's edge of human capability. the very limits of what our instruments can achieve. When engineers and scientists designed JWST, they aimed to reach into this epoch of cosmic dawn. The fact that the telescope has already succeeded in detecting something this far back is not just a technological triumph, but also a philosophical one. It suggests that no matter how faint or elusive the beginnings of the universe may be, human curiosity and ingenuity are relentless in pursuing them. MOM Z14, then, is not just another data point. It is a boundary marker, a reminder that we are standing on the edge of knowledge. Every photon it sends us has survived a journey longer than the lifespan of our planet, stretched and battered by the expansion of space itself, only to end its odyssey in the heart of our telescope. That survival alone makes it extraordinary, and the fact that it shines at such a redshift, at the very threshold of the observable, cements its place as one of the most remarkable finds in human history. To truly understand why MOM Z14's redshift is so astonishing, we must first break down what astronomers mean by redshift. At its core, redshift is the stretching of light as it travels across an expanding universe. When an object in space emits light, that light is composed of electromagnetic waves of various wavelengths. If the object is nearby, we can observe these wavelengths more or less as they are. But if the object is extremely distant, something fascinating happens. As the universe expands, the very fabric of space stretches, and with it, the wavelengths of light are stretched as well. This elongation pushes the light toward the redder end of the spectrum, the lower energy, longer wavelength side. Hence the term redshift. The redshift value, denoted as Z, is a way of quantifying just how much the light has been stretched. A small z means the object is relatively close, while a large z means the object is very far away and its light has been stretched enormously. For example, a redshift of z equals 1 means the universe has doubled in size since the light left its source. A redshift of z equals 6 places us in the realm of the early universe, when the first galaxies were beginning to form. But MOM Z14's redshift of z equals 14444 pushes into uncharted territory. It means that the universe has expanded by more than 15 times since the moment the galaxy emitted that light. We are effectively witnessing photons that left their birthplace when the cosmos was still a toddler, less than 2% of its current age. This measurement is groundbreaking for several reasons. First, it confirms that we are not just looking far away in space, but also far back in time. Because light has a finite speed, the farther it travels, the older the image we see. At z equals 1444, the light from MOM Z14 has traveled for 13.5 billion years. That is almost the entire history of the universe, interrupted only by the Big Bang itself. In practical terms, when JWST captures the light of MOM Z14, it is not just observing a galaxy, it is witnessing history itself, frozen in photons that began their journey before our planet even existed. Second, such a high redshift challenges the limits of detection. Light stretched this much no longer falls in the visible spectrum. Human eyes, or even the Hubble Space Telescope, cannot see it at all. The wavelengths have shifted into the infrared range, a part of the spectrum that can only be observed with specialized instruments like those aboard JWST. Without infrared sensitivity, MOM Z14 would remain invisible. Its existence demonstrates that the very design of JWST, its giant mirror, its cryogenic cooling systems, its infrared detectors, was not just aspirational, but essential for unlocking this level of cosmic history. Third, a redshift as extreme as z equals 14.44 tells us about the universe's rapid evolution. It compresses the timeline astronomers use to model how quickly matter could condense and ignite into stars. Normally, galaxies this early should be chaotic clouds of gas, with little organization. Yet MOM Z14 shows structure, suggesting that galaxy formation was happening far more rapidly than standard cosmology predicted. The redshift here is not just a number, it is a clue that the early universe was more efficient, more dynamic, and perhaps stranger than we thought. Finally, the concept of redshift carries profound philosophical weight. It means that the universe itself acts as a kind of cosmic time machine. Every redshifted photon is a messenger, carrying with it the story of expansion, distance, and age. MOM Z14 at Z equals 14.44 represents the upper reaches of this narrative. It tells us that no matter how vast the gulf of time and space, the universe leaves a record in its light, a record we now have the tools to read. So, when astronomers announce that MOM Z14 has a redshift of 14.44, they are not merely stating a technical detail. They are revealing a cosmic truth, that this faint galaxy existed at the very edge of the universe's dawn, and that we have succeeded in capturing its ancient light against all odds. In that number lies a connection between the deepest past and our present moment, a bridge across billions of years forged by the expansion of space itself. The story of galaxy formation is, in many ways, the story of the universe itself, learning how to build complexity out of chaos. In the immediate aftermath of the Big Bang, about 13.8 billion years ago, the universe was an almost featureless expanse of hot, dense plasma. Photons could not travel freely, as they were constantly scattered by free electrons in this opaque soup. Roughly 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. This milestone, known as recombination, allowed light to travel across space unimpeded, giving us the cosmic microwave background radiation we still observe today. But even then, the universe remained dark, without stars, galaxies, or anything resembling the structures we see now. The earliest galaxies were expected to form gradually, driven by the invisible scaffolding of dark matter. Dark matter, though unseen, dominates the mass of the universe, and its gravitational pull acted as the framework upon which ordinary matter could gather. Theoretical models predicted that small fluctuations in the density of dark matter would, over time, draw in hydrogen and helium gas. These gas clouds would collapse under their own gravity, sparking the first stars, and eventually forming the gravitationally bound systems we recognize as galaxies. But this was never thought to be an instant process. In fact, astronomers long believed that it would take several 100 million years, if not longer, for significant galaxies to emerge. The timeline usually presented was as follows. First, around 100 to 200 million years after the Big Bang, tiny stars known as population 3 stars would ignite. These stars, composed entirely of hydrogen and helium, were massive, short-lived, and incredibly bright, providing the energy needed to light up the cosmos. After they exploded as supernovae, they seeded their surroundings with heavier elements like carbon and oxygen. This enrichment of the interstellar medium allowed subsequent generations of stars to form with more stability. Only after many such cycles, spanning several 100 million years, were galaxies expected to take on recognizable shapes and begin accumulating enough mass and light to be visible across cosmic distances. And yet, the discovery of MOM Z14, just 280 million years after the Big Bang, threatens to rewrite this narrative entirely. It suggests that galaxy formation may have been far quicker and more efficient than once imagined. A system that is already luminous and organized at such an early epoch forces astronomers to question whether the initial conditions of the universe allowed structures to form faster, or whether our models underestimate the processes at work. For instance, could dark matter halos have formed earlier and been denser than predicted, accelerating the collapse of gas? Could star formation have been far more explosive and productive in the early universe, creating bright galaxies almost immediately after recombination? These questions shake the very foundation of our cosmological understanding. The prevailing lambda-cold dark matter model has been remarkably successful at explaining large-scale cosmic structures, the distribution of galaxies, and the growth of the universe. But discoveries like MOM Z14 highlight potential gaps. If galaxies this early are more common than expected, it could mean our assumptions about dark matter behavior, gas cooling rates, or even the physics of star formation are incomplete. Some theorists suggest that primordial black holes could have acted as seeds, drawing in matter more rapidly than dark matter alone. Others speculate that early regions of the universe may have varied more than anticipated, creating hotspots where galaxies formed unusually quickly. Another striking implication of MOM Z14 is its challenge to the idea of a long cosmic dark age. This was the epoch between recombination and the first stars, when the universe was thought to be lightless. The discovery of such an early galaxy implies that the darkness may have lifted sooner than expected. The cosmic dawn, the moment when starlight began to pierce through the fog of neutral hydrogen, might have arrived earlier, powered by the intense activity of systems like MOM Z14. Adding to the intrigue is the question of galactic maturity. MOM Z14 does not appear to be a mere blob of gas. It shows evidence of being a structured galaxy, bright enough to be observed across billions of light years. How could such maturity exist so early? If the first stars had only just begun to form, one would expect galaxies to be faint and disorganized. Instead, MOM Z14's brightness suggests rapid star formation on a massive scale, possibly far outpacing the efficiency of later galaxies like our own Milky Way. This raises profound questions about the nature of early star-forming regions and whether unknown processes accelerated their growth. It is also worth considering that MOM Z14 might not be unique. It may simply be the first of many such galaxies that JWST will uncover. If more galaxies with similar or even greater redshifts are detected, then the notion of early galaxy formation being an exception rather than a rule will collapse. We will be forced to accept that the universe was building galaxies almost immediately after recombination, compressing billions of years of expected development into mere hundreds of millions. Such a revision would have sweeping consequences, not only for cosmology, but also for our understanding of how elements, planets, and eventually life could emerge. The philosophical weight of this discovery cannot be ignored. For decades, astronomers thought they had a fairly coherent timeline. First came recombination, then the Dark Ages, then the first stars, followed much later by the first galaxies. MOM Z14 shatters this neat sequence. It tells us that the universe was capable of immense creativity in its earliest chapters, assembling luminous, structured galaxies in a cosmic blink of an eye. This forces us to ask, are we missing fundamental physics about how matter behaves under the extreme conditions of the early universe? Is there an aspect of cosmic evolution, perhaps linked to exotic dark matter interactions or previously unknown forces, that we have yet to uncover? MOM Z14 does more than simply extend the frontier of discovery. It acts as a provocateur, demanding that we revisit the assumptions we have held for decades. The birth of galaxies was never supposed to happen so soon, and yet here it is, evidence that the universe is far more efficient, more surprising, and more mysterious than we dared to believe. It is not simply a record breaker, it is a paradigm shaker, calling into question the very scaffolding of our cosmological story. The discovery of MOM Z14 is not only a triumph of science, but also a direct testament to the technological marvel that is the James Webb Space Telescope, JWST. Without JWST, this galaxy would have remained invisible, buried in the shadows of time, its faint light smeared into nothingness by the expansion of the universe. MOM Z14 sits so far away, so close to the dawn of creation, that only a machine designed with Webb-specific capabilities could possibly bring it into view. To grasp why this is true, we need to understand exactly what makes JWST unlike any telescope that came before. First and foremost is infrared sensitivity. As the universe expands, the light from distant galaxies is stretched, redshifted, until it no longer lies in the visible range. For something as distant as MOM Z14, the redshift is so extreme Z equals 14.44, that its light has been stretched into the deep infrared, invisible to human eyes and beyond the reach of telescopes like Hubble. Hubble, while revolutionary in its time, was primarily designed for ultraviolet and visible wavelengths, with only modest infrared capabilities. It could never have seen MOM Z14 because the galaxy's light lies far outside its detection window. JWST, on the other hand, was engineered precisely to capture these long, stretched-out wavelengths. Its primary mission is to probe the first billion years of cosmic history, and MOM Z14 is exactly the kind of discovery it was built to make. The telescope's massive segmented mirror also plays a crucial role. JWST's 6.5-meter diameter mirror is more than 2.5 times larger than Hubble's, giving it an extraordinary ability to gather faint light. The light from MOM Z14 has been traveling for 13.5 billion years, growing weaker with every passing eon. By the time it reaches us, it is so faint that only a telescope with a mirror of JWST's size and sensitivity could collect enough photons to reveal its presence. To put it simply, the larger the mirror, the deeper the gaze. JWST's mirror is like a giant hand stretched across space, catching the whispers of the earliest galaxies before they vanish into cosmic silence. Equally critical is JWST's cryogenic cooling system. In order to detect infrared light, the telescope must itself be colder than the objects it is observing. If JWST were warm, its own heat would drown out the faint signals of ancient galaxies like MOM Z14. That is why JWST is equipped with a massive 5-layer sunshield, the size of a tennis court, which blocks the heat of the Sun, Earth, and Moon. Operating at temperatures as low as 40 Kelvin, around 233 degrees, JWST becomes an exquisitely sensitive instrument, able to detect faint, ancient signals against the backdrop of the cold universe. Without this cooling, MOM Z14's fragile light would have been lost in the noise. Another advantage is its spectroscopic instruments, particularly the near-infrared spectrograph, NIR-SPEC, and the mid-infrared instrument, MIRI. These tools allow astronomers not only to detect galaxies, but to measure their redshifts with precision. In the case of MOM Z14, it was not enough to simply spot a faint smudge of light. Astronomers had to confirm its distance by analyzing the stretched wavelengths of its emission. Spectroscopy is the key to turning a blurry dot into a scientific treasure. By splitting the light into its component wavelengths, JWST reveals the fingerprints of hydrogen and other elements, confirming that the galaxy truly resides at the staggering distance corresponding to Z equals 1444. It's also worth emphasizing the stability and position of JWST. The telescope orbits around the second Lagrange point, L2, about 1.5 million kilometers from Earth, where the gravitational forces of the Sun and Earth balance in such a way that JWST can maintain a stable orbit with minimal fuel. From this vantage point, shielded from direct sunlight, JWST can observe the universe with unparalleled clarity and stability. Ground-based telescopes, despite their size, cannot match this because Earth's atmosphere blocks much of the infrared spectrum and distorts incoming light. Even the largest observatories on Earth would be blind to MOM Z14. This is why MOM Z14's discovery feels like the culmination of JWST's promise. For decades, astronomers dreamed of peering back to the cosmic dawn, when the first stars and galaxies flickered into existence. They knew Hubble could not do it, and ground telescopes would never suffice. Only a space-based observatory with a massive mirror, infrared instruments, cryogenic cooling, and the stability of deep space positioning could achieve such a feat. JWST was designed to answer the oldest questions. When did the first galaxies form? How fast did they grow? And what did the universe look like in its earliest chapters? MOM Z14 is the embodiment of that vision. In fact, MOM Z14 is so faint and so distant that even JWST is at its edge of capability. It represents not just a discovery, but a test of limits. By capturing this galaxy, JWST has proven that it can indeed probe the very edge of the observable universe, fulfilling its mission in the most dramatic way possible. Every photon collected from MOM Z14 validates the years of engineering, planning, and perseverance that went into building the telescope. It is no exaggeration to say that without JWST, MOM Z14 would still be a hidden ember of light, unseen and unknown. Ultimately, the role of JWST in this discovery is more than technical. It is symbolic. It demonstrates the extraordinary reach of human curiosity and ingenuity. From a small planet orbiting an ordinary star, we built a machine capable of looking back almost to the beginning of time itself. MOM Z14 is not just a distant galaxy, it is a gift delivered to us by JWST, a telescope that has turned the unimaginable into reality. The fact that we can witness such an object across 13.5 billion years shows that humanity has transcended the limits of its immediate world and extended its vision to the edge of creation. When we gaze at MOM Z14, we are not simply seeing a galaxy in space, we are seeing a galaxy in time. The light from MOM Z14 began its journey across the cosmos nearly 13.5 billion years ago, just a few 100 million years after the Big Bang. Every photon collected by the James Webb Space Telescope is a messenger from the dawn of cosmic history, carrying with it information about an era that no human eye, or telescope before JWST, had ever witnessed. To say that we are looking far away is true, but what makes it more profound is that we are looking far back. The deeper we look into space, the younger the universe becomes, until eventually we are staring at the very first moments of cosmic creation. This happens because the speed of light, though unimaginably fast, is not instantaneous. At about 300,000 kilometers per second, it takes light a finite amount of time to reach us. The moon's light takes a little over 1 second. Sunlight takes 8 minutes. Light from the nearest star, Proxima Centauri, takes over 4 years. Now extend that idea to a galaxy so distant that its light has been stretched across the expanding universe for over 13 billion years, and you begin to grasp the magnitude of what it means to see MOM Z14. We are witnessing it not as it is today, but as it existed in its infancy, when the universe was just beginning to take shape. That perspective transforms astronomy into a kind of time machine. MOM Z14 is not just a faint smear of light in JWST's data. It is a living snapshot of the universe's childhood, frozen in time and carried to us across the vastness of space. The galaxy we see is impossibly ancient, yet it is still here in our view, preserved by the speed limit of light and the expansion of space. Observing it is akin to opening a window into a cosmic memory that would otherwise be forever lost. The fact that we can retrieve this memory at all feels like an act of defiance against the passage of time. When we place MOM Z14 on the cosmic timeline, its significance becomes even more staggering. The universe is about 13.8 billion years old, and this galaxy formed roughly 280 million years after the Big Bang. In human terms, that would be like looking back not just at an ancestor, but at the very first heartbeat of civilization itself. Most galaxies we see today are mature, sprawling structures filled with billions or even trillions of stars. But MOM Z14 represents something more delicate, the fragile beginnings of structure, the first clumping of gas and dust into something that would one day shine as a galaxy. What makes this backward gaze so powerful is the realization that the universe is layered in time, not just in space. Every star we see, every galaxy, every flicker of light in the night sky exists at its own point on the cosmic timeline. Some are close and familiar, showing us the universe as it is now. Others, like MOM Z14, are impossibly remote, offering a glimpse of what the universe once was. In this way, astronomy is unlike any other science. It does not merely study objects in the present, it reconstructs the past by capturing the light that has traveled across eons. But MOM Z14 pushes this principle almost to its limit. With a redshift of 14.44, it belongs to an era when the universe was still cloaked in hydrogen fog, a time known as the cosmic dark ages, giving way to reionization. To look at it is to see the universe as it first turned on its lights. Galaxies like this are believed to be the engines of cosmic transformation, their first stars pouring out radiation that burned away the primordial mist and made the universe transparent. Without such galaxies, the universe might have remained a dark, opaque expanse for far longer. What's even more astonishing is that the light we detect today has been stretched, distorted, and weakened by the expansion of space itself. The original ultraviolet light from young, hot stars in MOM Z14 has traveled across an expanding universe, stretching into the infrared spectrum by the time it reached us. That is why telescopes like JWST, built specifically to detect infrared light, are indispensable. Without its powerful infrared eyes, MOM Z14 would remain invisible, its ancient signal buried under the glow of nearer, brighter galaxies. What we see today is not just light, it is ancient history, bent and redshifted by the growing fabric of the cosmos. When you consider that we are looking at MOM Z14 as it was more than 13 billion years ago, another realization dawns. The galaxy itself has not stood still. The photons we see are old, but MOM Z14 has continued to evolve over the billions of years since. Today, if it still exists, it may look nothing like the faint, compact galaxy JWST captured. It could have merged with neighbors, grown larger, or even been torn apart by cosmic collisions. Yet, in our eyes, it will always remain young, a fossilized portrait of a moment that can never be repeated. Looking at MOM Z14 is therefore more than an act of astronomy. It is a confrontation with time itself. It reminds us that the universe is not static but dynamic, that everything we see is in motion, changing, and fleeting. It reminds us of our place in this vast chronology, where human history spans mere seconds compared to cosmic time. And above all, it forces us to grapple with the enormity of creation itself. That in the dim afterglow of the Big Bang, galaxies already found a way to ignite, to cluster, and to shine. MOM Z14 is not just the oldest galaxy ever observed. It is a messenger from the edge of time, whispering the story of how everything we know began. To look at it is to look back into the universe's earliest memories, to glimpse a chapter that shaped the rest of cosmic history, and to feel the weight of 13.5 billion years pressing into a single point of light. The discovery of MOM Z14 takes us directly into what astronomers call the cosmic dawn, a poetic term for one of the most transformative eras in the history of the universe. This was the moment when the cosmos transitioned from darkness into light, when the very first stars and galaxies emerged to pierce the endless void left behind after the Big Bang. For hundreds of millions of years following that initial explosive beginning, the universe was a strange, dim place, filled mostly with neutral hydrogen gas. There were no galaxies, no stars, no structures of the kind we recognize today. Just a vast, expanding cloud of matter, waiting for gravity to weave it into something more. As time passed, tiny ripples in the density of matter, seeded by quantum fluctuations in the earliest moments of the Big Bang, began to grow. Under the slow but relentless pull of gravity, clumps of gas collapsed inward, heating up as they compressed. Eventually, some of these collapsing pockets of hydrogen reached the extreme conditions necessary to ignite nuclear fusion. And with that, the first stars were born, the beginning of light in a universe that had been cloaked in darkness for millions of years. These first stars, called Population 3 stars, were unlike anything we see in the modern cosmos. They were enormous, many hundreds of times the mass of our Sun, short-lived and incredibly bright. They burned furiously, lived briefly, and ended their lives in titanic explosions that scattered the very first heavy elements, like carbon, oxygen, and iron into the universe. Without these primordial stars, galaxies could never have formed, and life as we know it could never have existed. The cosmic dawn was not just the birth of light, it was the birth of structure itself. Those first stars grouped together, their gravity pulling in more gas and forming the earliest galaxies. MOM Z14, seen only 280 million years after the Big Bang, is one of these trailblazers. Observing it is like opening a time capsule from the moment the universe was first switching on its lights. It tells us that galaxy formation began shockingly early, far earlier than many scientists had expected. The prevailing models once suggested that it would take several 100 million years for enough material to come together to form fully fledged galaxies. Yet MOM Z14 sits there as undeniable proof that the universe wasted no time in forging its first luminous cities of stars. This era is also tied closely to another great transformation: reionization. After the Big Bang, the universe was filled with neutral hydrogen, which absorbed ultraviolet light and kept everything shrouded. But when the first stars and galaxies began shining, their radiation had the power to ionize that hydrogen, essentially tearing electrons away from atoms and turning the universe transparent. This epoch of reionization was the great unveiling, allowing light to travel freely across space and making the universe visible in a way it hadn't been before. MOM Z14 belongs to this epoch, perhaps even contributing to the reionization itself. That means we are not just looking at a distant galaxy, but at one of the key players that helped turn on the cosmic lights for everything that followed. The cosmic dawn is important for another reason. It reminds us that the universe is not static, but alive, changing, and evolving. When we look at MOM Z14, we are not simply seeing an ancient object frozen in time. We are glimpsing the first steps of an ongoing story, one that eventually led to the galaxies we see today, to the formation of planets, and ultimately to us. Every star in our sky, every atom in our bodies, every galaxy swirling in the cosmos can trace its existence back to this dawn. Without that early ignition of stars, there would have been no chemical enrichment, no galaxies, no complex structures, only an endless, empty darkness. And perhaps most astonishing of all is the thought that we are now, billions of years later, able to study that very beginning. The fact that light from MOM Z14 has traveled 13.5 billion years across space and time to reach us is almost unfathomable. That fragile signal, stretched by cosmic expansion into the infrared spectrum, carries within it a record of the moment when the universe first awakened. JWST's instruments have turned this faint light into something tangible, allowing us to reconstruct the story of cosmic dawn with breathtaking detail. In essence, the discovery of MOM Z14 proves that the cosmic dawn was not a slow, tentative flicker, but a rapid blaze. The universe was eager to create, to shine, to build. And by capturing this galaxy at such an extreme distance, we now have a front-row seat to that first awakening. It is as if we are watching the universe take its very first breath, illuminating a path that would eventually lead to galaxies like our Milky Way and to observers like us, pondering it all across the gulf of time. The discovery of MOM Z14 forces astronomers to reconsider assumptions they once thought were secure. For years, the accepted narrative placed the birth of the first galaxies somewhere between 300 to 500 million years after the Big Bang, a time when matter had cooled and clumped enough to ignite the first sustained bursts of starlight. Yet MOM Z14, shining just 280 million years after the universe began, stands as a luminous contradiction to that story. Its very existence suggests that galaxies could assemble, grow, and shine far more quickly than theory had ever anticipated. Models of cosmic evolution will now need to account for a universe that was more efficient, more dynamic, and perhaps more chaotic than textbooks have described. This discovery does more than shuffle dates on a cosmic timeline. It reshapes the entire understanding of the pace of creation. The physics of how stars formed out of hydrogen clouds, how those stars enriched their surroundings with heavier elements, and how they merged into galaxies suddenly must be rewritten to allow such rapid development. If MOM Z14 was already glowing so early, then the first stars must have ignited almost immediately after conditions allowed, in numbers and densities once thought impossible. Theories of star formation that relied on slow cooling processes or extended collapses of matter may no longer hold. Instead, astronomers may need to imagine far more violent, efficient mechanisms at work in the early cosmos. The textbooks also face another uncomfortable revision: the role of dark matter. Conventional wisdom places dark matter as the invisible scaffolding that allowed gas to gather and form galaxies over time. But MOM Z14's youth raises the possibility that dark matter halos were far more effective than predicted in drawing matter together. Perhaps their gravitational pull clumped hydrogen so quickly that galaxies could form in a fraction of the expected time. If true, then the properties of dark matter itself, its distribution, density, and interactions, may need to be reassessed. A small, faint galaxy like MOM Z14 has now become a testing ground for questions as vast as the nature of the unseen matter that makes up most of the universe. Even the concept of cosmic dawn, once thought to be a gradual glow spreading across hundreds of millions of years, might need to be sharpened into a sudden blaze. If galaxies like MOM Z14 lit up the sky earlier than predicted, then reionization, the process that turned the universe from opaque to transparent, may have happened faster, driven by a greater abundance of early galaxies than astronomers assumed. The old picture of a slow and steady dawn may now be replaced by one of a dramatic, almost immediate ignition of cosmic light. This discovery also challenges what we thought we knew about the kinds of stars that existed in these galaxies. Astronomers expected the first stars to be massive, short-lived, and composed almost entirely of hydrogen and helium. Yet for MOM Z14 to shine so brightly so soon, it must have already contained multiple generations of stars, suggesting cycles of birth, death, and enrichment occurred with astonishing speed. That implies that heavy elements, carbon, oxygen, iron, were forged and scattered into space far earlier than anticipated. The chemistry of the universe, too, may have raced ahead of schedule. In essence, MOM Z14 is not just a faint smudge on JWST's detectors. It is a message from the past, whispering that the universe was more restless, more urgent, and more alive in its infancy than we had ever dared to believe. Every chapter of astronomy that deals with the birth of stars, the rise of galaxies, and the unfolding of the first billion years will now need to be rewritten. Astronomers will have to revisit simulations, adjust models, and perhaps accept that their view of cosmic evolution has been too conservative. What this galaxy proves is that the universe is capable of surprise, even at its earliest moments. Every step we take to look further back in time does not simply confirm what we think we know. It exposes the limits of that knowledge. MOM Z14 forces us to acknowledge that the cosmos is not bound by our timelines or expectations. It builds faster, burns brighter, and challenges us to continually reshape the way we tell the story of everything. When we turn our attention to the size and scale of MOM Z14, we begin to appreciate the almost paradoxical nature of this galaxy. On one hand, it is the most ancient and distant galaxy ever observed, existing only 280 million years after the Big Bang, a time when the universe itself was still in its infancy. On the other hand, despite its youth on the cosmic clock, MOM Z14 is far from small or insignificant. Its mass, luminosity, and apparent star-forming activity defy expectations for a structure so early in the universe's history, making it a true enigma in astronomy. To understand its size, we must begin by comparing it with the galaxy we know best, our own Milky Way. The Milky Way is a massive spiral galaxy stretching about 100,000 light-years across, containing an estimated 200 to 400 billion stars, with a total stellar mass of around 1 trillion solar masses when factoring in its dark matter halo. MOM Z14, in comparison, is nowhere near this scale. Early measurements suggest that its size is more modest, likely just a few 100 million solar masses in total, and perhaps spanning only a few thousand light-years across. To put that into perspective, it is smaller than the Large Magellanic Cloud, a dwarf satellite galaxy of the Milky Way. Yet, what makes MOM Z14 extraordinary is not its absolute size, but rather the fact that it managed to assemble this much mass so early in cosmic history. This is where the puzzle deepens. Standard cosmological models have long suggested that galaxies in the early universe would begin as small, faint, irregular structures, slowly merging over billions of years to form the grand spirals and giant ellipticals we see today. But MOM Z14 seems to leap ahead in that timeline. By existing with such significant mass and brightness at a redshift of 14.44, it demonstrates that star formation and galactic assembly happened much faster than many simulations predict. Instead of being a faint, barely detectable smudge of light, MOM Z14 is bright enough that JWST's NARCam was able to clearly register its signal. This brightness indicates vigorous star formation taking place within its bounds. Astronomers estimate that MOM Z14 is undergoing a period of rapid stellar production, a so-called starburst phase. Starburst galaxies are characterized by intense, short-lived episodes of star formation, where hundreds or even thousands of solar masses worth of stars are born every year. While the exact rate in MOM Z14 is still being refined, early data suggests it is forming stars at an astonishing pace for such an early galaxy, potentially dozens of solar masses per year, if not more. To appreciate that, compare it with the Milky Way, which produces only about 1 to 2 solar masses worth of new stars annually. This means MOM Z14 is forming stars far more aggressively than our galaxy does today, despite being much smaller in scale. Brightness, in turn, is a direct consequence of this stellar birth frenzy. Young, massive stars burn incredibly hot and emit copious amounts of ultraviolet light, which gets stretched into the infrared by the time it reaches JWST. The observed luminosity of MOM Z14 tells astronomers that these stars are present in great numbers, pouring energy into their environment. The galaxy likely shines brightly against the dark canvas of the early universe, its light traveling more than 13.5 billion years before arriving in JWST's mirrors. The size of MOM Z14 also raises intriguing questions about its structure. While modern galaxies like the Milky Way are well-organized systems with spirals, bulges, and halos, galaxies this early in cosmic history were often chaotic, irregular, and still assembling. MOM Z14 may not have the orderly disk-like structure of today's galaxies, but instead could be a clump of star-forming regions bound together by gravity. Its compactness may actually help explain its brightness. Light from so many stars packed into a small region can make it appear more luminous than it might otherwise if spread out. Dark matter, too, plays a key role in shaping the galaxy's size and gravitational stability. Like all galaxies, MOM Z14 must reside in a dark matter halo, a kind of invisible framework that gives it the gravitational scaffolding necessary to hold its stars and gas together. For it to exist so early, dark matter halos must have collapsed very quickly after the Big Bang, gathering baryonic matter, the ordinary matter that makes up stars and planets, into dense enough clumps to ignite star formation. The size of MOM Z14 thus becomes a clue not just about galaxy formation, but also about the behavior of dark matter and its role in structuring the early universe. Comparing MOM Z14's mass and luminosity with other early galaxies discovered by JWST also highlights its uniqueness. Prior to this, galaxies like Glass Z13 or GN-Z11 held the record for earliest known galaxies, but their redshifts were slightly lower, around Z=13 and Z=11, respectively. Those galaxies, too, appeared surprisingly massive and bright for their time. But MOM Z14 pushes this trend to the extreme, existing even earlier while still managing to exhibit significant star formation. This forces astronomers to question whether the universe's first galaxies formed in a more accelerated fashion than we once believed, or whether our models need to incorporate new physics, perhaps more efficient cooling of primordial gas, or unexpected behavior in how stars and black holes seeded the early cosmos. Another aspect of MOM Z14's size relates to its potential for future growth. Galaxies at this stage of the universe's history were constantly colliding and merging, assembling larger structures over time. MOM Z14 could represent one of the first building blocks of what would later become a massive galaxy. In fact, if we were able to fast forward billions of years, MOM Z14 might eventually merge with others to form a galaxy not unlike our own Milky Way. What we see today is only the beginning of its story. In summary, MOM Z14 may not rival the Milky Way in raw scale, but the fact that it is as large, bright and star-forming as it is, so soon after the Big Bang, makes it a true anomaly. Its mass demonstrates that galaxy assembly was happening at lightning speed. Its brightness reveals a thriving population of young stars, defying expectations of a dim, primitive system. Its compactness suggests it was a dense, energetic furnace of creation. Taken together, the size of MOM Z14 serves as a reminder that the early universe was not as quiet and gradual as once thought, but a turbulent, fast-paced crucible of cosmic construction, where galaxies like this one blazed into existence long before anyone thought possible. The discovery of MOM Z14 doesn't just open a window into early galaxy formation. It also raises the tantalizing possibility that within its faint light, we may be glimpsing the fingerprints of the very first stars ever born. These hypothetical stars, known as population 3 stars, represent one of the most elusive and sought-after mysteries in all of cosmology. Unlike any stars we see in the universe today, population 3 stars were forged directly from the primordial gas left behind after the Big Bang. They had no heavy elements, no carbon, no oxygen, no iron, nothing that we take for granted in stars like our Sun. Instead, they were born from a universe composed almost entirely of hydrogen and helium, the simplest and lightest elements, created in the first 3 minutes of cosmic history. Astronomers believe that population 3 stars were monstrously large compared to modern stars, perhaps hundreds of times more massive than the Sun. With such enormous masses, they would have burned ferociously hot and bright, but lived incredibly short lives, lasting only a few million years before exploding in violent supernovae. These explosions seeded the universe with heavier elements, paving the way for population 2 and population 1 stars, the later generations, which include the Sun. Without the first stars, galaxies as we know them could not have formed. Every rock, planet, tree, and person owes their existence to that initial generation of stellar furnaces that produced the building blocks of chemistry beyond hydrogen and helium. Now, when we look at MOM Z14, we are peering back just 280 million years after the Big Bang, so close to the dawn of time that the conditions for population 3 stars may still have existed. Could MOM Z14 harbor them? The galaxy's light, faint and stretched across the cosmic void, holds potential clues. If the stars within it were truly metal-free, meaning they lacked heavier elements, then their spectra would look very different from the stars we know today. They would radiate with an intense ultraviolet glow, their enormous masses pumping energy into their surroundings and possibly driving the reionization of the universe, the process that transformed the cosmos from a dark, neutral fog into a transparent, light-filled expanse. But detecting these signatures is no easy task. The light we see from MOM Z14 has been redshifted by a factor of 14.44, stretched far into the infrared. What might once have been blazing ultraviolet emissions now arrive at Earth as faint whispers of infrared radiation. JWST's instruments are designed to capture precisely this kind of stretched starlight, and astronomers are now scouring the galaxy's spectrum for telltale signs. One of the major clues would be the absence of metals. If researchers can find convincing evidence that the galaxy contains stars devoid of heavy elements, it could be the first strong case for population 3 stars ever observed. However, there's another twist. By the time MOM Z14 came into being, the universe had already gone through nearly 300 million years of evolution. Some models suggest that by then, the very first population 3 stars may have already lived and died, enriching the cosmos with their explosive ashes. If that were the case, then MOM Z14 might not be home to pure population 3 stars, but rather their immediate descendants, stars made from gas that had just been touched by the first heavy elements. In that scenario, MOM Z14 could represent a transitional stage, a cosmic halfway point where the universe was just beginning to shift from the age of the first stars into the age of complex galaxy formation. Still, the possibility cannot be dismissed. The early universe was not uniform. Different regions may have evolved at different rates, with some pockets of primordial gas collapsing into stars before others. MOM Z14 could be one of those late forming pockets, where the first metal-free stars ignited much later than elsewhere. If so, then studying this galaxy could provide a rare laboratory to witness the final flickers of the population 3 era. If population 3 stars do exist within MOM Z14, the implications are enormous. We would be looking at the direct ancestors of every star that has come since. The discovery would validate decades of theoretical work and give astronomers an unprecedented opportunity to study how the first light of the cosmos shaped everything that followed. It would also help refine our understanding of reionization. These stars, with their immense ultraviolet output, were likely critical in burning away the cosmic fog that once cloaked the universe. Confirming their presence would be like catching the first rays of dawn in a night that had lasted hundreds of millions of years. Even if MOM Z14 does not contain population 3 stars, its existence is still revolutionary. It proves that galaxies were forming rapidly, earlier than most models predicted. And if it turns out that MOM Z14 is made entirely of later generation stars, that would still tell us something profound. That the first stars must have lived, died, and enriched the universe incredibly quickly, perhaps within the first 100–200 million years after the Big Bang. Either outcome forces a revision of our cosmic timeline. The search for population 3 stars has been described as astronomy's holy grail. For decades, telescopes have hunted for their chemical fingerprints in nearby stars, in distant galaxies, and in the cosmic background itself. None have been found with certainty. MOM Z14 now offers the best chance yet. It sits on the razor's edge of the universe's youth, glowing faintly across time, carrying within it the possibility that we might finally see what the first stars looked like. If we confirm them, the story of the cosmos becomes clearer. A universe born in darkness, illuminated first by these titanic, short-lived giants, and then gradually populated with the smaller, more familiar stars and galaxies we know today. If we don't, the mystery deepens. Perhaps the first stars burned too fast, too hot, and too early for us ever to glimpse them directly. Either way, MOM Z14 ensures that the quest to find the first stars has entered its most exciting chapter yet. The discovery of MOM Z14 does not merely add another point to astronomy's growing list of high redshift objects. It calls into question the very framework of how galaxies were expected to emerge and evolve in the first place. For decades, standard cosmological models have suggested that galaxy formation was a slow, gradual process, dictated by the accumulation of dark matter halos, followed by the cooling of baryonic gas, and the eventual ignition of stars. The understanding has always been that the earliest galaxies were small, faint, and irregular, struggling to form under the chaotic conditions of a young universe. Yet, MOM Z14, emerging just 280 million years after the Big Bang, appears surprisingly mature, bright, and star-forming, a revelation that unsettles many of the assumptions built into these models. In the conventional timeline, after the universe's first 100 million years, the earliest dark matter halos began attracting clouds of primordial gas. This process was not expected to be efficient enough to produce luminous galaxies for several 100 million years more. Instead, theory predicted a gradual assembly of matter, where countless small protogalactic fragments would later merge over billions of years to form the grand spirals and ellipticals we observe today. Galaxies at redshifts greater than 10 were expected to be rare, dim, and disorganized, mere seeds of the giants to come. Yet, MOM Z14 is neither invisible nor insignificant. Its brightness and inferred mass hint at a galaxy that had already managed to overcome the limitations of cosmic infancy, defying the sluggish pace theory had long dictated. One of the most striking challenges posed by MOM Z14 lies in its apparent mass. For such a galaxy to exist so early, a vast amount of gas had to cool and collapse into stars at a rate much faster than models currently allow. Star formation requires the cooling of hydrogen gas, often mediated by elements like carbon and oxygen, which were scarce in the primordial universe. If MOM Z14 truly formed stars so quickly, it suggests either that star formation was more efficient than we imagined, or that the physics guiding these early processes unfolded in ways our models have failed to capture. This points to a universe that may have been far more dynamic, turbulent, and capable of rapid structure formation than the neat equations of standard cosmology suggest. Another layer of contradiction emerges when considering the concept of feedback. In theory, early star formation should have been self-limiting. The first stars, especially if they were massive population 3 stars, would have unleashed torrents of ultraviolet radiation, heating and ionizing the surrounding hydrogen. This radiation should have slowed down further star formation, preventing galaxies from reaching substantial sizes so quickly. Yet MOM Z14 seems to have sidestepped this bottleneck, continuing to grow despite what should have been suppressive feedback loops. This implies that either the universe's gas reservoirs were far more abundant and resilient to feedback effects than expected, or our understanding of how early radiation and gas interactions shaped cosmic evolution is incomplete. Cosmologists are now left to grapple with the possibility that their models may underestimate the role of dark matter in the earliest times. Dark matter halos, invisible scaffolds that guide the growth of galaxies, may have formed faster and grown more massive than simulations suggest. If so, they could have provided deeper gravitational wells that allowed gas to condense into stars far earlier. Alternatively, some have speculated about exotic physics, possibilities such as variations in dark matter behavior, or even tweaks to the cosmological constants that underpin the universe's expansion. While such ideas remain speculative, MOM Z14 demonstrates that reality has already outpaced the predictions of safe cosmology. What makes the challenge sharper is that MOM Z14 is not alone. Other high redshift galaxies, discovered in recent years by JWST, have also shown themselves to be brighter and more massive than the models predicted. MOM Z14, however, sets a new record, existing even closer to the Big Bang than its predecessors. Each new discovery in this category adds weight to the argument that galaxy formation happened in a more accelerated, chaotic, and efficient manner than cosmologists have allowed. The consistency of this pattern cannot be easily dismissed as observational error or statistical fluke. It demands serious reconsideration. In the grand picture of cosmic history, MOM Z14 may force astronomers to rewrite the early chapters of the universe's timeline. Rather than a long dark age where galaxies slowly struggled into existence, we may be looking at a cosmos that erupted into brilliance far sooner, with galaxies assembling rapidly in the wake of the first stars. This does not just affect how we think about star and galaxy formation. It reshapes our understanding of reionization, the growth of large-scale structure, and even the role of dark energy and dark matter in shaping the infant universe. Perhaps the most profound contradiction is philosophical. The universe, according to our best models, should not have been ready to build something like MOM Z14 so soon. Yet here it is, blazing from nearly 13.5 billion years ago. A reminder that the cosmos continues to humble us by refusing to fit neatly into our equations. It is as though the universe itself is saying that while models are necessary, reality is richer, faster, and stranger than we can yet comprehend. In the presence of MOM Z14, cosmology must face its limits and evolve, just as galaxies themselves once did in the early dawn of time. When we talk about MOM Z14, we are not just speaking about an ancient collection of stars. We are glimpsing a possible participant in one of the greatest transitions the cosmos has ever undergone: cosmic reionization. To understand why this matters, we need to step back into the dark ages of the universe, a time after the Big Bang, but before the first stars flickered into existence. Roughly 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine, forming the first neutral atoms of hydrogen and helium. With no bright stars or galaxies yet, the cosmos was a vast, cold, and dark ocean of neutral gas. Photons, which had once scattered freely, now traveled largely unimpeded, leaving behind the faint glow we see today as the cosmic microwave background. But this darkness was not permanent. Something had to ignite the universe again. Something had to light the skies. And that moment is what astronomers call the epoch of reionization. MOM Z14, forming just 280 million years after the Big Bang, sits right inside this critical period. The very existence of such a galaxy means that it may have been part of the great process of ripping apart the cosmic fog of neutral hydrogen. When the first stars and galaxies began to shine, they emitted torrents of ultraviolet light energetic enough to ionize hydrogen atoms, knocking electrons free from protons. This transformation of the universe's gas from neutral to ionized was not instantaneous. It happened gradually, patch by patch, as the ultraviolet light from many young galaxies carved glowing bubbles of ionized hydrogen into the surrounding darkness. Eventually, these bubbles grew, overlapped, and merged, until the universe was once again transparent, open, and luminous. Without this transformation, galaxies, stars, and planets as we know them could never have emerged into clear view. The critical question is whether galaxies like MOM Z14 were numerous and powerful enough to drive this process. For years, astronomers have debated what supplied the energy for reionization. Were massive, brilliant galaxies like MOM Z14 the main contributors? Or was it instead a multitude of smaller, fainter galaxies that together produced enough ultraviolet light to complete the task? MOM Z14's brightness suggests that even at such a young age, some galaxies were far more active than models had predicted, capable of flooding their surroundings with ionizing radiation. If MOM Z14 formed vast clusters of stars rapidly, then it might have been one of the cosmic torches that burned holes through the darkness. But there is also the possibility that MOM Z14 contained some of the universe's very first, most massive stars, the fabled population 3 stars, composed of only hydrogen and helium. These stars, far larger and hotter than our Sun, would have been prodigious producers of ultraviolet light, making them prime candidates for fueling reionization. If galaxies like MOM Z14 were filled with such stars, then they were not just faint glimmers in the void. They were engines of cosmic transformation. Understanding MOM Z14's role in this epoch could reshape our models of early structure formation. If this galaxy was already thriving just 280 million years after the Big Bang, then perhaps cosmic reionization happened faster or with more intensity than we have long assumed. It forces astronomers to ask whether the timeline of the Dark Ages and the dawn of light is shorter than imagined, compressed by the rapid rise of galaxies like this one. And beyond the technical questions lies a poetic truth. Every photon from MOM Z14 that reaches our telescopes today is a survivor of that ancient battle between light and darkness. Each particle of light carries the memory of a time when the universe was breaking free from its primeval fog, when the first galaxies were not just forming, but reshaping the very nature of the cosmos. To see MOM Z14 is to witness one of the candles that lit the universe for the very first time. The discovery of MOM Z14 stands as one of the faintest glimmers of light humanity has ever managed to pull from the depths of the cosmos. To see it at all is a marvel, for the galaxy lies so far away that its photons began their journey over 13.5 billion years ago, crossing an expanding universe, stretched and reddened by the relentless passage of time. By the moment they reached JWST's detectors, those photons were no longer in the visible light spectrum, but stretched into infrared wavelengths, like ancient whispers barely clinging to existence. That faintness is not just a detail, it is a crucial limit marker, a boundary line showing how far our instruments can reach into the abyss. MOM Z14 pushes JWST to its very edge, revealing both the astonishing sensitivity of the telescope and the immense difficulty of capturing light from such a distance. The faintness of MOM Z14 cannot be overstated. Compared to a galaxy like the Milky Way, which shines with hundreds of billions of stars and produces an intense outpouring of radiation across the spectrum, MOM Z14 is like a candle flickering against a storm. It is small, dim, and faint, producing light that has been scattered and stretched nearly beyond detectability. In fact, astronomers debate whether JWST even captured its full picture. What we see may just be the brightest part of a galaxy whose fainter outskirts are lost entirely to the noise of the background universe. This reminds us that while JWST has extraordinary capabilities, it is still bound by the harsh rules of physics, optics, and cosmic distance. Even with its unmatched resolution and infrared reach, there are limits to how far and how faint it can go. MOM Z14 is a beacon at the very frontier of those limits. When astronomers say JWST detected MOM Z14, they are not talking about a crisp, colourful spiral like the galaxies closer to us. Instead, the galaxy appears as a faint smudge, a barely distinguishable dot in a sea of black. Yet inside that dot lies an entire world of stars, possibly star clusters and clouds of primordial gas. It forces astronomers to pass tiny fragments of light, stretching the telescope's detectors to extreme sensitivity, teasing out patterns from what could otherwise be lost to the noise of space. The feat of detection is not merely technological, but philosophical. It raises the question of how many more galaxies remain unseen, too faint even for JWST to glimpse. If MOM Z14 is visible at this limit, then perhaps beyond it lies a far larger population of galaxies from the first ages, still hidden, just beyond the grasp of our most powerful eye. The faintness also exposes the challenges of observational astronomy. When scientists push the telescope toward its ultimate sensitivity, they encounter the cosmic infrared background, an unavoidable haze created by the glow of dust and galaxies across billions of years. This background acts like a fog, obscuring faint objects. Detecting MOM Z14 means astronomers had to work at the razor's edge of data analysis, separating its tiny signal from the cosmic haze. The fact that they succeeded tells us both how remarkable JWST's instruments are and how much fainter galaxies must exist that we cannot yet reach. MOM Z14, then, is not just a discovery. It is a threshold, telling us that we may be standing on the edge of the observable dawn. What does this limit mean for the future of astronomy? It shows us both the immense triumph of JWST and its constraints. MOM Z14 demonstrates that we can push back the veil of time to nearly 280 million years after the Big Bang. But going beyond that, to 200 million, 150 million, or closer to the very first stars, may demand instruments even more powerful. The faintness of MOM Z14 suggests that truly primordial galaxies, smaller and dimmer than this one, may remain hidden for now. This means JWST might only be seeing the tip of the cosmic iceberg. If MOM Z14 is one of the brightest galaxies of its time, what about the thousands of dimmer siblings we cannot yet detect? They could be the true architects of cosmic reionization, quietly shaping the early universe while remaining invisible to us. There is also the question of gravitational lensing, a phenomenon where massive foreground objects, like galaxy clusters, bend and magnify light from distant galaxies behind them. Some of the faintest galaxies detected before were spotted thanks to lensing, their light boosted by cosmic magnifying glasses. MOM Z14, however, was seen directly, without lensing, meaning it was bright enough, even across 13.5 billion years, to stand alone in JWST's field of view. This reinforces how unusual it is. For every MOM Z14 we can see, countless others may remain hidden without the cosmic assistance of lensing. The faintness thus speaks not only to the limits of our vision, but also to the quirks of cosmic geometry that sometimes let us peek further than we should. The limits of detection are not just a matter of brightness, but also of precision. The further back we look, the more light is redshifted, stretched into longer wavelengths. By the time photons from MOM Z14 arrived, they had been shifted deep into the infrared, where the telescope must sift them out with exquisite accuracy. JWST's instruments, like NIRCam and NIRSpec, were built specifically for this task, tuned to the ancient red glow of the first galaxies. Yet even they have boundaries. Beyond a certain redshift, the signal becomes too faint, the noise too overwhelming, and the interpretation too uncertain. MOM Z14 lies right at that frontier, almost daring us to go further. This faintness also forces humility. Astronomy is not a complete picture, but a mosaic of fragments. MOM Z14 is one piece of that mosaic, but it is likely incomplete. What we see may be just the brightest portion of its structure, the rest lost to darkness. Our instruments do not yet give us the full story. They give us glimpses. And these glimpses remind us that the cosmos is far vaster, far more populated than what we can detect. The faint galaxies, the hidden stars, the dim companions, they are out there, shaping the universe in ways we can only imagine. MOM Z14 marks the faintest flicker we have caught so far, but it is also a promise of what remains unseen. In this way, the faintness of MOM Z14 is both a triumph and a frustration. It demonstrates JWST's staggering sensitivity, but also highlights the need for future telescopes, perhaps even ones like the proposed Habitable Worlds Observatory or the even more ambitious LUVOIR, to reach deeper, fainter, and earlier. We are brushing against the first light of creation, but not yet touching its very beginning. MOM Z14 is not just a galaxy, it is a boundary marker, showing where our vision ends and mystery begins. Beyond its faint light lies the uncharted darkness, where the first galaxies flickered to life, waiting for instruments that can one day pierce even deeper into the past. When comparing MOM Z14 with earlier record holders such as GLASS Z13, one begins to see just how fast the James Webb Space Telescope is overturning what we thought we knew about the early universe. GLASS Z13, discovered not long ago, made headlines because it appeared to be one of the earliest galaxies ever observed, existing roughly 320 million years after the Big Bang at a redshift of Z13. Its detection was a monumental achievement at the time, marking a boundary of human vision into cosmic history that had seemed nearly unreachable. Yet, in the blink of an eye, science has moved from celebrating GLASS Z13 to standing in awe at MOM Z14, a galaxy not just slightly, but meaningfully earlier in time, shining from only about 280 million years after the universe began. The leap from Z13 to Z1444 may sound like a small numerical difference, but in terms of cosmic chronology, it represents tens of millions of years closer to the universe's true dawn. In that primordial context, even such a short time span carries staggering implications. It shifts the timeline of cosmic history backward, telling us galaxies were assembling faster, earlier, and with more structure than theories allowed. Glass Z13 itself had already begun to strain models. Its size and brightness suggested a galaxy surprisingly massive for its age, forcing astronomers to consider whether the rules governing star formation were more efficient in the early universe than expected. But MOM Z14 raises the stakes. Compared directly, MOM Z14 sits deeper in time, older by tens of millions of years, yet it seems to show levels of luminosity, mass, and star formation activity comparable to, or even beyond, glass Z13. In other words, MOM Z14 is not just an earlier version of what we already saw in glass Z13. It appears as a full-fledged, functioning galaxy, contradicting the idea that such structures needed more time to form. The very existence of MOM Z14, so shortly after glass Z13, suggests galaxies did not just appear gradually. They emerged explosively, carving themselves into the fabric of space far sooner than theory predicted. This rapid rewriting of cosmic records underscores the power of JWST. Where the Hubble Space Telescope once struggled to see faint smudges at redshifts of 7 or 8, JWST is now effortlessly pushing to 13, 14, and beyond. The pace of discovery feels almost dizzying. First came glass Z13, which itself seemed extraordinary. Then within months, MOM Z14 claimed the crown, pushing the observational frontier tens of millions of years closer to the Big Bang. If the trend continues, we may soon find galaxies at Z equals 15 or 16, existing less than 250 million years after the beginning of time. Each new step backward doesn't just fill in a missing chapter, it erases the assumptions of the chapters we thought we had written. It reveals the story of cosmic dawn as more compressed, more chaotic, and more vibrant than ever imagined. When set side by side, the two galaxies demonstrate an almost poetic narrative of progress. Glass Z13 was found in JWST's early release science program, using the GLASS Grism Lens Amplified Survey from Space, collaboration's observations of distant fields. Its discovery came as a delightful surprise, proof that JWST was not only working, but already over-delivering. MOM Z14, however, emerged from a dedicated effort to scour JWST's deepest imaging, one of several campaigns designed to reach the absolute limits of what the telescope can reveal. The fact that MOM Z14 surfaced so quickly after glass Z13 shows that the early universe is richer than anyone dared hope. Rather than one rare, isolated galaxy existing at such a time, we may be seeing the first hints of a population, meaning galaxies were common at redshifts beyond 13, not freak accidents of early formation. The comparison also highlights how the differences between these galaxies force us to ask new questions. Why does MOM Z14 appear even brighter relative to its age? Does it suggest that galaxy-building mechanisms, like rapid gas collapse or unusually efficient star formation, were already well underway so soon after the Big Bang? Or does it hint at more exotic possibilities, like alternative models of dark matter or physics beyond the standard cosmological framework? Glass Z13 was the opening act, challenging us to tweak our models. MOM Z14 is the encore, suggesting we may need to throw out the script entirely and begin again. Together, they show a progression not just of discovery, but of discomfort. The realization that the universe refuses to conform neatly to our timelines. On a human level, the contrast between glass Z13 and MOM Z14 serves as a reminder of how quickly scientific milestones can fall. In the past, records for the oldest galaxy would stand for years, sometimes decades, before a new telescope or instrument pushed the frontier further. But in the JWST era, It seems those records last mere months. The telescope's unmatched infrared sensitivity and resolution are accelerating the pace of astronomy, making discoveries that once felt like once-in-a-generation events now almost routine. Glass Z13 barely had time to be enshrined in textbooks before MOM Z14 demanded revisions. It is a thrilling, almost disorienting time in astronomy, where history is rewritten in real time. In the grander sense, comparing these galaxies also emphasizes the extraordinary nature of JWST itself. Both Glass Z13 and MOM Z14 lie so far away that their light has been stretched and dimmed by cosmic expansion to a whisper. Yet JWST, parked 1 million miles from Earth at the L2 point, can still capture that light and deliver it to us with clarity. The fact that we are now directly observing galaxies within the first few 100 million years after creation is something that astronomers a generation ago would have considered science fiction. The telescope's ability to vault from Glass Z13 to MOM Z14 in such a short time highlights not only the richness of the universe, but also the staggering leap in our technological capacity to see it. Ultimately, the story of Glass Z13 and MOM Z14 is not one of competition, but of continuity. They are milestones on a path that is leading us inexorably closer to the first flickers of starlight, to the elusive population of galaxies and stars that truly marked the universe's awakening. Each discovery builds upon the last, forming a ladder into the past. Glass Z13 was a vital rung, showing that galaxies existed earlier than expected. MOM Z14 is the next, reaching still further back, hinting that the ladder continues, and that still older galaxies await our gaze. The comparison between them illustrates not just what we have learned, but the thrilling promise of what lies ahead, the likelihood that we have not yet glimpsed the true edge of cosmic dawn. And as JWST continues to peer deeper, the record set by MOM Z14 may be as fleeting as that of Glass Z13, soon replaced by even older discoveries, each one a new challenge to our understanding of how everything we see around us first began. The confirmation of MOM Z14 as the oldest known galaxy in the universe was not something that happened overnight or through a single observation. It required a symphony of astronomical techniques, the most crucial being spectroscopy, the science of studying light and breaking it down into its constituent wavelengths. This process is at the very heart of modern astronomy because, while telescopes can capture images of faint smudges of light from across the cosmos, those images alone cannot tell us their age, distance, or composition. To unlock those secrets, astronomers must analyze the spectrum, the fingerprint of the universe etched in light itself. When the James Webb Space Telescope first detected MOM Z14, it appeared as a faint red glow. This redness was not because the galaxy itself is intrinsically red, but because its light had been stretched by the expansion of the universe, a phenomenon known as redshift. At a staggering redshift of ZT equals 14.4, the light we are seeing today left MOM Z14 nearly 13.5 billion years ago, only 280 million years after the Big Bang. But in astronomy, seeing a red dot is only the beginning. Proving its redshift requires painstaking measurements. That's where spectroscopy comes in. JWST's Near-Infrared Spectrograph, NIR-SPEC, was designed precisely for such tasks. This instrument disperses incoming light into its component wavelengths, producing a spectrum much like a prism, splitting white light into a rainbow. In that spectrum, astronomers look for telltale markers, sharp dips or spikes caused by atoms and molecules absorbing or emitting light at specific energies. These spectral lines act like cosmic barcodes. Hydrogen, the most abundant element in the early universe, leaves a particularly distinct signature, and it is often used as a reference point. For MOM Z14, astronomers searched for the Lyman alpha break, a sudden drop in light at certain wavelengths caused by hydrogen gas absorbing photons above a specific energy threshold. Detecting the Lyman break in MOM Z14's spectrum was a smoking gun. This break had been shifted deep into the infrared part of the spectrum due to the galaxy's extreme redshift, exactly as theory predicted for an object so ancient. This confirmed that the galaxy wasn't some closer object masquerading as a distant one, such as a dusty star-forming galaxy or a cool star in the Milky Way. Instead, the spectroscopy provided undeniable proof. MOM Z14 truly resided in the universe's first 2% of history. But spectroscopy did more than just confirm distance. It also hinted at the galaxy's composition and star-forming activity. Even at such great distances, astronomers could detect signs of intense star formation, revealed by the brightness of the galaxy's ultraviolet continuum. By measuring the slope of that ultraviolet light, scientists can infer the rate of star birth within the galaxy. For MOM Z14, the readings suggested a surprisingly active stellar nursery, where young, massive stars burned hot and bright, despite the short time available to assemble such a system. The process of capturing this light, however, was anything but easy. At Z equals 1444, the galaxy's photons are incredibly stretched and dimmed, requiring JWST's unmatched sensitivity. The telescope had to collect light over long exposures, stacking faint signals to distinguish them from background noise. Even so, astronomers had to be extremely cautious, double and triple checking that what they were seeing was not a statistical fluke or contamination from a foreground object. Sophisticated algorithms and cross-checks against other instruments on board JWST, such as NIRCam, near-infrared camera, helped ensure reliability. This meticulous approach reflects the broader philosophy of astronomy. Extraordinary claims require extraordinary evidence. When glass Z13 was discovered, there was excitement but also skepticism, as the evidence then relied on photometric redshift estimates, measurements based on broad color filters rather than direct spectra. Such estimates can sometimes be misleading, especially when galaxies are faint or dusty. But MOM Z14 went a step further. Its redshift was spectroscopically confirmed, making it far more secure as a record holder. This not only established its place in cosmic history, but also raised the bar for what counts as a true discovery of an ancient galaxy. What makes this all the more astonishing is that JWST is effectively reaching the very limits of what we can observe. Spectroscopy at these redshifts pushes technology to its breaking point. Each faint photon arriving from MOM Z14 had been traveling for nearly the entire history of the cosmos, dodging dust, gas, and gravitational distortions along the way, before finally landing in JWST's detectors. The fact that we can decode such ancient whispers of light into meaningful science is nothing short of miraculous. Looking deeper, these techniques also shed light on the conditions of the universe itself during the galaxy's birth. By studying the absorption features in the spectrum, astronomers can learn about the intergalactic medium, the vast stretches of gas between galaxies. At this early epoch, the universe was undergoing reionization, when the first stars and galaxies ionized neutral hydrogen that filled the cosmos. MOM Z14's light carried with it the imprint of this transformation, encoded in the subtle shapes of its spectral lines. Thus, confirming MOM Z14's redshift wasn't just about measuring distance, it was about peering into the very fabric of the young universe. Each spectral line, each drop in light, each faint photon told a story billions of years in the making. Astronomy, at its core, is about reading these stories written in light, and spectroscopy is the language that makes it possible. With MOM Z14, that language spoke loud and clear. Galaxies were forming faster, earlier, and more vigorously than our theories had dared to imagine. When astronomers confirmed the existence of MOM Z14, it was more than just another scientific milestone. It was a promise of what might still lie ahead. The James Webb Space Telescope has already stretched the boundaries of observation to unprecedented distances, unveiling galaxies that existed less than 300 million years after the Big Bang. But the discovery of MOM Z14 raises an even deeper question. If we can see this galaxy at redshift 1444, how much farther can Webb truly go? And could there be galaxies even older, sitting silently in the cosmic dawn, waiting to be found? The truth is, MOM Z14 is likely not the first galaxy that ever formed. It is simply the first one we have been able to detect so far. Every observation is limited not by the universe's possibilities, but by the tools we use to observe it. JWST, with its 6.5-meter segmented mirror and infrared sensitivity, was built for this kind of challenge. It is specifically designed to peer into the early universe by catching the faint red-shifted glow of galaxies whose light has been stretched by more than 13 billion years of expansion. Yet even JWST has its limits. The cosmic dawn, the period between roughly 100 and 500 million years after the Big Bang, remains largely unexplored territory. If MOM Z14 formed just 280 million years after the beginning, then there could be galaxies hiding at redshifts of 16, 18, or even 20, corresponding to a universe barely 200 million years old. These galaxies would represent the very first clumps of matter collapsing under gravity, igniting the earliest stars that relit the cosmos. Detecting them would not just be about pushing technical limits, it would mean witnessing the universe's first steps toward complexity. Future surveys with JWST are already being planned to hunt these extreme galaxies. Programs like Cosmos Web, SEERS, Cosmic Evolution Early Release Science, and JADES, JWST Advanced Deep Extragalactic Survey, are systematically mapping the faintest, most distant galaxies across wide patches of sky. The deeper JWST looks, the more likely it is to stumble upon even older structures, galaxies that may redefine how quickly matter organized after the Big Bang. MOM Z14's discovery was made possible by an ambitious survey targeting regions of space dense with faint light sources. By extending these efforts, astronomers hope to identify additional galaxies that lie just beyond the current redshift frontier. But the question of what comes next isn't just about finding older galaxies. It's about refining the techniques to prove their distances. With GLASS Z13 and now MOM Z14, astronomers have demonstrated that photometric redshifts, the rough estimates made by analyzing the color of galaxies, can suggest candidate galaxies from the early universe. But spectroscopy, the detailed study of light's fingerprint, is essential for confirmation. JWST's NIR-SPEC and NIR-CAM instruments have already proven capable of this task. But as galaxies get fainter, the challenges of separating genuine ancient light from cosmic noise increase dramatically. This means that future surveys must push not only in depth, but also in precision. Another frontier is the search for signatures of population 3 stars, the very first generation of stars made purely of hydrogen and helium. If JWST can catch evidence of their presence within galaxies even earlier than MOM Z14, it would solve one of astronomy's greatest mysteries. What did the very first light sources look like? Detecting such stars directly may be nearly impossible due to their short lifespans, but their fingerprints might still linger in the chemical composition of galaxies at extreme distances. This is one of the key goals of ongoing and future JWST campaigns. Looking ahead, astronomers are already imagining what comes after JWST. Telescopes like the Nancy Grace Roman Space Telescope, set to launch later in the 2020s, will complement Webb's deep vision with wide-field surveys, increasing the odds of catching rare early galaxies. Even further in the future, concepts like the Habitable Worlds Observatory or LUVOIR, Large UV Optical IR Surveyor, could extend humanity's reach into the very first 100 million years of cosmic history. MOM Z14 may be the beginning of a new golden age in cosmology, a stepping stone to uncovering galaxies that existed when the universe was still in its infancy. Yet for now, JWST remains our best tool for piercing the cosmic veil. Each new deep field image, each painstakingly analyzed spectrum, and each carefully selected target field could reveal galaxies that push the timeline further back. MOM Z14 was a reminder that the universe always holds surprises, and that every time we think we've reached the limit, reality forces us to rethink. The next galaxy JWST uncovers may lie just a little farther, a little fainter, and a little older, rewriting cosmic history yet again. The implications of this ongoing search are profound. If we find galaxies at redshift 16 or beyond, it means that star formation began almost immediately after the first atoms formed, compressing the universe's timeline in ways that challenge current models. It would imply that the seeds of structure were planted earlier and grew faster than standard cosmology allows. On the other hand, if JWST eventually fails to find galaxies older than MOM Z14, it might suggest that we are indeed closing in on the true beginning of starlight, the last barrier between the dark, primordial universe and the light-filled cosmos we know today. What's next for JWST is not just a matter of discovery, it's a matter of perspective. Each faint glimmer it detects carries us closer to the ultimate frontier, the moment the universe first awoke. And with every record-breaking galaxy it finds, we are reminded that the story of cosmic origins is still being written, one photon at a time. MOM Z14 exists at a staggering redshift of 14.44, which corresponds to a time only about 280 million years after the Big Bang, a blink of an eye on cosmic timescales. This places it perilously close to what astronomers call the edge of the observable universe, the ultimate boundary beyond which light has not yet had enough time to reach us. The concept of the observable universe is not about the absolute size of the cosmos, but rather about the limits imposed by the speed of light and the finite age of the universe. Since the universe is roughly 13.8 billion years old, the farthest we can theoretically observe is limited to the distance light has traveled during that time. But because space itself has been expanding during those billions of years, the true boundary of the observable universe is not 13.8 billion light-years away. It is closer to 46 billion light-years in radius. MOM Z14 sits near this extreme limit, like a whisper from the very dawn of creation. When astronomers look at MOM Z14, they are not merely looking far away, they are looking back in time. The light from this galaxy has been traveling across expanding space for over 13.5 billion years before finally arriving at JWST's detectors. That means the galaxy we see is not as it exists now, but as it was in its infancy. In reality, MOM Z14 may have evolved dramatically since then, possibly merging with other galaxies, growing larger, or even ceasing to exist in any recognizable form. But the image we see today is locked in the past, frozen like a photograph of a child who has long since grown into an adult. That is the profound irony of studying galaxies near the edge of the observable universe. We can only ever see their youth, never their maturity. The placement of MOM Z14, so close to the observable edge, raises intriguing questions about the true scale of cosmic history. How many other galaxies are out there, hidden in the unobservable depths of the universe, their light forever beyond our reach? If MOM Z14 represents one of the first well-formed galaxies, then it suggests that structures were emerging astonishingly quickly after the Big Bang. But could there be galaxies even older, lying at redshifts of 15, 16, or beyond, so faint and so distant that even JWST cannot detect them? If so, then the edge of our cosmic vision is not defined by the absence of galaxies, but by the limitations of our instruments. In other words, the observable edge is as much a technological horizon as it is a physical one. To place MOM Z14 into context, astronomers must reckon with the strange nature of cosmological distances. The redshift of 14.44 means that the universe was only about 2% of its current age when the light left that galaxy. But because of cosmic expansion, the actual distance between us and MOM Z14 today is far greater than the number of years its light has traveled. Astronomers estimate that the current co-moving distance to MOM Z14 is well over 30 billion light-years. That number alone is staggering. A galaxy we see in its infancy, barely 280 million years into cosmic history, now lies tens of billions of light-years away due to the relentless expansion of space. This stretching of space is what creates the observable universe's boundary, a shifting, ever-growing edge that places galaxies like MOM Z14 at the very brink of what we can detect. The edge of the observable universe is not static, it evolves as time passes. Each year, new shells of light from ever-distant galaxies reach us, expanding our horizon slightly. But there will always be regions that remain forever beyond visibility. The accelerated expansion of the universe, driven by dark energy, ensures that some galaxies will slip permanently out of view, receding faster than their light can ever reach us. MOM Z14, despite being within our current observational reach, reminds us of this delicate balance between visibility and invisibility. It is a messenger from a fleeting moment in time, one that future astronomers millions or billions of years from now may never be able to observe at all, as cosmic expansion pulls it irrevocably away. This proximity to the cosmic edge makes MOM Z14 not just a scientific discovery, but also a philosophical one. It forces us to ask whether the universe we can observe is truly representative of the whole. If galaxies like MOM Z14 existed so early and so abundantly, then perhaps the unseen universe beyond our horizon is teeming with even more primordial structures. It is a humbling thought that our most powerful telescope has shown us wonders at the limits of visibility, yet may still be missing entire realms of galactic activity hidden just past the cosmic curtain. Furthermore, MOM Z14 challenges the idea of a simple, gradual progression of galaxy formation. The fact that such a luminous, structured galaxy emerged so early suggests that galaxy-building processes were highly efficient, or that we are witnessing the visible tip of an iceberg of hidden early galaxies. If this is true, then the edge of the observable universe is not merely a boundary of distance, but a threshold into a hidden epoch of cosmic history. Galaxies may have been forming in significant numbers even before the 280 million year mark, but their light is stretched and dimmed beyond what we can detect. MOM Z14, then, could be the first hint of an unseen multitude lurking at the very beginning of time. There is also the poetic reality that the observable universe is, by definition, unique to each observer. An alien civilization in a galaxy billions of light-years away would have its own observable horizon, encompassing galaxies we cannot see, while excluding some that we can. To them, MOM Z14 might not even exist in their observable sky, while to us, it is a groundbreaking discovery. This relativity of cosmic perspective highlights just how fragile and precious our window into the universe truly is. MOM Z14 is not just a galaxy, it is a fleeting gift of alignment, timing, and technology, allowing us to glimpse what lies at the very boundary of knowability. Ultimately, the discovery of MOM Z14 underscores that the edge of the observable universe is not an end, but a beginning. It is a frontier that calls to us with mysteries we may never fully unravel. For every galaxy like MOM Z14 that we uncover, there are surely countless more waiting beyond the veil, hidden not because they do not exist, but because the universe's rules of light and time forbid us from ever reaching them. And yet, this limitation is what makes MOM Z14 so extraordinary. It reminds us that, against staggering odds, humanity has managed to pierce the darkness and glimpse creation itself, standing at the very brink of visibility, staring into eternity. Dark matter has long been one of the great mysteries of cosmology, invisible yet profoundly influential, a silent architect sculpting the large-scale structure of the universe. When astronomers look at galaxies like MOM Z14, formed only about 280 million years after the Big Bang, they aren't just studying starlight. They're peering into the scaffolding of dark matter itself, the hidden web upon which luminous matter hangs. The discovery of MOM Z14, so early and yet so well structured, forces cosmologists to reconsider how quickly dark matter halos could have collapsed and drawn in gas to form stars and galaxies. For decades, theoretical models have suggested that dark matter is the cosmic backbone, forming giant halos that attract ordinary matter through gravity. Without it, galaxies would never have had enough time to assemble in the early universe. In the prevailing picture, tiny fluctuations in the density of the universe after the Big Bang gradually grew under the influence of dark matter. Over hundreds of millions of years, these fluctuations became gravitational wells that trapped gas, igniting the first stars and galaxies. But the timeline has always been a sticking point. According to models, it should take several 100 million years before a galaxy as luminous and structured as MOM Z14 could appear. Yet here it is, already glowing brilliantly at just 280 million years after the cosmic dawn. The presence of MOM Z14 suggests that dark matter halos formed and collapsed even faster than expected. Perhaps dark matter clumps grew more rapidly, or maybe their gravitational pull was more efficient at concentrating baryonic matter, the normal atoms of hydrogen and helium, into dense pockets where star formation could occur. If this is true, it implies that the interaction between dark matter and regular matter was stronger or more immediate in the early universe than previously modeled. Some theorists even speculate that dark matter itself may not be entirely inert. Could it have properties, still undiscovered, that made early galaxy formation easier? MOM Z14 also helps astronomers probe the nature of dark matter candidates. For decades, physicists have debated whether dark matter is made of cold, slow-moving particles, cold dark matter, or CDM, warm, slightly faster particles, warm dark matter, WDM, or something even stranger. In the CDM model, small-scale structures form early, merging to create larger galaxies over time. This fits reasonably well with MOM Z14's early appearance, suggesting that dark matter was indeed cold and able to clump efficiently soon after the Big Bang. Warm dark matter, on the other hand, smooths out small-scale fluctuations, delaying galaxy formation. If MOM Z14 is representative of many galaxies at this epoch, it may deal a blow to warm dark matter theories, because galaxies shouldn't have appeared so quickly in that scenario. Yet, the puzzle isn't fully solved. The brightness and star formation rate inferred for MOM Z14 are almost too high for even cold dark matter models. It may be that MOM Z14 represents an extreme outlier, a statistical rarity, but if future surveys find many galaxies at similar or even higher redshifts, the standard cold dark matter framework will come under renewed scrutiny. The universe, it seems, is telling us that galaxies didn't wait patiently for eons to form. They exploded into being at a pace our equations still struggle to explain. The structure of MOM Z14 also hints at how dark matter might shape galaxies differently in the early universe compared to the present day. In nearby galaxies, dark matter forms vast halos that extend far beyond the luminous disk, providing the gravitational glue that keeps stars from flying apart. In MOM Z14, the halo must have been incredibly dense and compact, given how quickly it pulled matter together. That compactness may explain why early galaxies are often observed to be much smaller in size than modern ones, despite being so bright. They are packed with stars in a tiny space, compressed by the intense gravity of their halos. Another implication of MOM Z14's discovery lies in the cosmic reionization epoch, the time when ultraviolet light from the first stars and galaxies ionized the fog of neutral hydrogen that filled the young universe. For reionization to occur so early, galaxies had to form efficiently, producing enormous amounts of energetic light. Dark matter halos, by acting as the cradles of early galaxies, played a decisive role. The fact that MOM Z14 was already luminous enough to contribute suggests that dark matter halos were not just present, but highly effective at catalyzing star formation at this critical stage. Some researchers are now considering alternative models of dark matter. For instance, self-interacting dark matter, SIDM, proposes that dark matter particles occasionally bump into one another, redistributing energy and perhaps accelerating the collapse of halos in the early universe. Could this explain why galaxies like MOM Z14 appeared so soon? Or could it be that dark matter interacts weakly with radiation or normal matter in ways we haven't yet detected, seeding galaxies even faster than we thought? These are not idle questions. Each new observation of galaxies at extreme redshifts feeds back into particle physics, pushing scientists to refine, rethink, or even abandon long-standing theories. MOM Z14 also touches on the tension between simulations and reality. In computer models of the early universe, dark matter halos form hierarchically. Small ones appear first, merging into larger structures over time. But MOM Z14 seems to be already massive, bright, and highly star-forming far too early. Either the simulations are missing key physics, or the nature of dark matter itself is different than assumed. This has led some cosmologists to consider exotic alternatives, like fuzzy dark matter, ultra-light particles with quantum wave-like properties that might alter how structure forms on small scales. Though controversial, these models are receiving renewed attention in light of discoveries like MOM Z14. Perhaps the most profound implication is that galaxies like MOM Z14 are not merely observational curiosities. They are laboratories for dark matter physics, offering windows into how the invisible backbone of the universe shaped everything we see today. By mapping the abundance, brightness, and clustering of early galaxies, astronomers can constrain what dark matter is, how it behaves, and why the universe looks the way it does. Each faint smudge of light captured by JWST isn't just a galaxy, it's a fingerprint of the unseen majority of the cosmos. In the end, MOM Z14 serves as a stark reminder. We are still in the early stages of deciphering dark matter's secrets. We can trace its gravitational pull, infer its presence from galactic rotation curves, gravitational lensing, and cosmic microwave background fluctuations. But we cannot see it directly, nor do we know what it's made of. And yet, thanks to galaxies like MOM Z14, we are slowly learning how it sculpts the universe, from the first sparks of starlight to the grand spiral galaxies of today. The discovery may not solve the mystery of dark matter, but it provides a crucial clue. Whatever dark matter is, it enabled galaxies to bloom astonishingly early, rewriting the story of cosmic dawn in ways both thrilling and humbling. From the perspective of a human being standing on Earth, it is almost impossible to grasp the immensity of what discoveries like MOM Z14 represent. We are creatures bound by days and nights, by the rhythm of our planet's orbit around the Sun, by memories that rarely stretch beyond a handful of generations. Yet somehow, from this tiny vantage point, we have extended our sight back to a time when the universe itself was only a few 100 million years old. That is not just science. It is a profound act of imagination, of curiosity, of daring to ask questions that reach beyond the limits of human scale. What makes this even more humbling is that we are not peering at something nearby, like a mountain or an ocean, but at the very origins of existence itself. Every photon captured by the James Webb Space Telescope from MOM Z14 began its journey long before Earth had formed, long before the Sun had ignited, long before even the Milky Way existed in its present shape. And yet, those photons patiently crossed a changing, expanding universe until at last they reached a human-made mirror, orbiting in the quiet dark beyond our planet's atmosphere. To think that we, as fragile and finite beings, could arrange atoms into a telescope capable of receiving such an ancient signal is staggering. In moments like this, the boundary between science and philosophy blurs. We are reminded that the universe is not just out there, it is a story we are part of. The light we see from MOM Z14 is not separate from us. It is connected to the same laws of physics that forged the atoms in our bodies. The hydrogen that made its stars and the hydrogen that fuels our sun share the same origin. We are, in a very real sense, the universe trying to look at itself. And perhaps the most astonishing thought of all is this: we are only at the beginning. If we can already see this far back with today's instruments, what might future generations discover? Could they peer even closer to the Big Bang, into the mysterious first moments where time and space themselves were being born? Could they uncover not only galaxies, but the very seeds of structure, the faint traces of how everything we know came to be? From this little world, the universe feels limitless, both in space and in possibility. Standing under the night sky, it is easy to feel small, but discoveries like MOM Z14 reveal that smallness is not weakness, it is a vantage point. From our tiny planet, we are proving that the human mind can transcend its limits, that our vision can stretch across billions of years, and that our hunger to know will always push us closer to the edge of eternity. The universe may be vast, but with every discovery, we bring its story a little closer to home. MOM Z14 stands in the cosmic record not merely as a distant smudge of light, but as a relic, a fossil etched into the very fabric of the universe. Its faint glow, arriving across nearly 14 billion years of stretching space, is the echo of creation itself. To behold, it is to pierce the veil of time and touch the fragile infancy of everything we know. Long before galaxies like our Milky Way unfurled their spirals, before stars like the Sun ignited their steady fires, before Earth even dreamed of forming, MOM Z14 was already blazing, stitching the first patches of light into the great quilt of night. And so, when the James Webb Space Telescope caught that flicker, it was not merely detecting another galaxy, it was intercepting memory, light released when the universe was barely more than a newborn, still humming with the afterglow of the Big Bang. MOM Z14 carries in its glow a testimony of firsts, the first stars collapsing into brilliance, the first elements weaving together into complexity, the first stirrings of structure in an otherwise formless sea. It is as though the cosmos itself left behind a diary entry from its earliest days, and only now, at the pinnacle of human ingenuity, have we managed to read it. There is something profoundly humbling in this, for we, tiny creatures on a pale blue planet orbiting a mediocre star, have built mirrors polished enough and instruments sensitive enough to capture the oldest whispers of the universe. Out of all the infinite darkness, we have learned to read the faintest traces of light. We do not just observe MOM Z14, we join it in its endurance. Its journey across cosmic epochs mirrors our own journey to understanding, both marked by perseverance against overwhelming odds. And as we gaze at it, there is a strange intimacy between the infinite and the fragile. We are bound by the same laws of physics that birthed its stars. The same atoms forged in its furnaces now course through our blood. MOM Z14 is not separate from us. It is part of our ancestral chain, a luminous ancestor whose starlight carved the road toward the possibility of life itself. To call it a galaxy feels insufficient. It is a monument carved in photons, a time capsule older than imagination, a fossilized flame preserved in the boundless night. It reminds us that the universe is not only vast, but also ancient, and that within its enormity are the origins of every heartbeat, every thought, every dream that has ever existed. And so we close on this truth. MOM Z14 is not just a galaxy. It is a glimpse into creation's first breath, a shimmering fossil from the universe's childhood. Its light, fragile yet eternal, is a reminder that even the smallest flicker can survive the darkness of eternity, and that by looking outward, we are, in fact, looking back at the very moment everything began. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.